So I would like to introduce the next speaker. And he's Hugo Duminil-Copin from the University of Geneva. And Hugo graduated at 2012. And only in 2 years, he was promoted to full professor at the University of Geneva. And he received many prizes, including the Davidson Prize, and the Oberhofer Prize, and also the earlier Kurt Prize from Mathematical Physics Association. So he has done many spectacular work, including this one on the honeycomb lattice conductivity, which has this famous constant square root 2 plus square root 2, and also in many problems in critical phenomena for Ising and percolation models. So let's welcome Hugo.
Okay, is it? Yeah, seems to be working. Well, so thank you very much for the invitation. It's really a pleasure to be speaking here. So since I have 2 talks, I thought I would be doing the following. The first talk is going to be more of an overview of a few of my results. And basically, the idea is that I would like to introduce a very classical model called the Potts model, which is one of the most classical models in statistical physics. Try to spend a little bit of time defining it and motivating it, and telling you a little bit about one problem that you can, one question that you can ask about this model. And this question is going to be our silver lining for what is going to happen afterwards. Because what I really want to illustrate is that this Potts model is a specific case of what we call a lattice spin model. And in the last 50 years, lattice spin models have been studied using many different tools in mathematics, from algebra to analysis, and passing also by probability. And I want to present to you, to advertise to you, a probabilistic approach to lattice spin models via what we call the geometric representations of these models. And I will try to present 2 of them. So there will be really a first part on the definition, and then a second part on one representation, and a third. So these 2 will be basically the first talk. And the third section will correspond to the second talk, and it will be yet another geometric representation that I'm going to describe. So what I will try to do is in the second talk, I'm going to be using the blackboard and try to really put a little bit more my hands in the system and really try to show you a few proofs. Okay, but the first part is going to be more colloquium style and try to give you a motivation of what is happening. Very good. So what is the Potts model, and why do we want to introduce such a model? So in the end of the 19th century, Pierre Curie made a very nice experiment and discovered what we call the Curie temperature for ferromagnets. So what is it? It's just that if you take a magnet and you heat it sufficiently at sufficiently high temperature, it's going to lose its magnetization. And if it cools down again, then it's going to regain its magnetization. So it goes from a paramagnetic, from a ferromagnetic to a paramagnetic state. So actually, you can do the experiment. I mean, if you do it with iron, you need to go up to like 700 degrees, which is not necessarily a good idea. But actually, you can buy online some special magnets, not made of iron, but on some alliage of different metals. And then you only need to heat it at 100 degrees. So I bought these things and thought, OK, it's going to be a great experiment in front of everybody. But I still thought, OK, maybe I should be a little bit afraid, so I'm going to try at home. And I both burned myself and triggered the fire alarm. So I thought this was not a good experiment to make in front of you. So you will have to just trust me that even with a lighter now and the right magnet, you can actually unmagnetize a magnet. So that was Curie's experiment. And in 1920, Lenz proposed a model to just explain this loss of magnetization. And this model was based on 3 main features. The first one is that it was a lattice model. So what you imagine is that your magnet is made of atoms which are on a crystalline lattice, say ZD, these 3. Then you consider that every point in every vertex in your lattice has a spin. It's either pointing plus in the plus direction or in the minus direction. They really act like small magnets. And the third thing that you want to, the third feature is that you want your model to be ferromagnetic. So you want to mimic the fact that magnets have a tendency to point in the same direction. So what you want is that neighboring vertices, the spins of neighboring vertices prefer to be pointing in the same direction. So either both plus or both minus. So I'm going to tell you exactly what the definition of the model is. But I mean, from this idea, he came up with this model, which unfortunately for him was not named after him, but after Ising, who was one of his PhD students. And this is one of the most studied models in statistical physics. So I'm not going to really define just the Ising model. I'm going to directly define a generalization of this model. So instead of imagining that at every vertex you have two spins, plus or minus, I'm going to decide that, in fact, I have a color among Q colors. So for Q equal 2, it's exactly the same as the Ising model. You just, plus is one color, minus is the other color. So every vertex of my graph is going to receive a color sigma x. And the configuration in my model will be just a coloring of my graph. Okay? So I'm giving myself the color at every vertex. So now I'm a statistical physicist, so what I want is I want to sample at random a coloring of the graph. And I want to keep in mind these ferromagnetic features that I was describing for the Ising model, that here in this case I would like vertices at neighboring, pairs of neighboring vertices to have a tendency to have the same color, basically. So what I'm going to do, I'm going to define the energy of a configuration to simply be the number of neighboring vertices which have different colors. So the larger this number, the larger the energy. And now I'm going to say, okay, the probability of a configuration sigma is going to be inversely proportional to this energy. So I'm going to say it's proportional to exponential of minus 1 over t times the energy. So the larger the energy, the smaller the probability. This constant z is just here to make this a probability measure. Notice that t here is a parameter. It's just a positive number. And it gives you a little bit how much you care about this ferromagnetic force. In particular, you see, if you take t equals 0, this 1 over t becomes minus 1 over t becomes minus infinity. So this is going to become the Dirac, just the uniform measure on configuration with minimal number of disagreements, smallest energy. So in this case, it's just a monochromatic configuration. So for t equals 0, this is just a uniform measure on monochromatic configurations. So there are Q of them. On the other hand, if t tends to infinity, this 1 over t tends to 0, and you just get the uniform measure on every configuration. You do not care at all anymore on about the energy. Okay? So this t is tuning somehow how much you care about the energy. Now, what is the question that you want to ask? Well, what you want to ask is whether, I told you, okay, this energy is made in such a way that two spins that are, two neighboring vertices, well, we expect that the spin has the colors have a tendency to be the same. But is it true if you take points far away from each other? And in particular, take G to be larger and larger, and take points to be farther and farther away from each other, do they still have a tendency to be of the same color or not? So let's try to translate that mathematically. So let's take a graph, take a subgraph of ZD. And I want to break the symmetry because it's not going to be very convenient for us. So I want to break the symmetry between all the colors. So what I'm going to do is I'm going to favor color 1. And I do that as follows. This is the boundary of my graph. It's just the vertices in my graph that are connected, that are neighbors of a vertex which is not in my graph. And I'm going to define almost the same measure as before, except that in the energy, I'm adding a new term, which is a number of points on the boundary which do not have the spin, the color equal to 1. Okay? So I'm adding this thing, which is breaking the symmetry between all the colors. And if you think about it, it's exactly equivalent to doing the following. Outside of your graph, you just put color 1, and you look at the number of disagreements, of disagreeing pairs of vertices. It's exactly the same. So it's a little bit like you are saying, I'm conditioning everything outside my graph to be color 1, and now I'm looking at the measure induced on my graph. So of course, if you fix G, what do you expect? If you look at the probability at 0, say, let's say that 0 is 1 over, or at any vertex x in my graph, the probability that this vertex has color 1, well, it's not going to be 1 over q anymore because I'm favoring these 1s on the boundary. So it's going to be larger than 1 over q. But now imagine you take a G to be a box, a big box. Let's say your vertex is the origin, and let the box go to infinity. So for every finite size of the box, of course you want, the probability of 0 to be of color 1 is going to be larger than 1 over q. But somehow maybe when you push the boundary conditions to infinity, then this force that the boundary is enforcing on your spin at 0 is going to be weaker and weaker. And maybe at the end you lose the symmetry breaking. You recover symmetry when you take the size of your lattice, of your graph to infinity. But maybe not. And the answer, in fact, depends on the temperature. So let's say you define, in order to let the size go to infinity, I need to tell you somehow to tell you what I mean by letting n goes to infinity, the size of your graph go to infinity. Well, you will have to trust me that these measures, when you let G tend to the full lattice, it converges weakly to a certain random coloring of the full lattice of ZD. It's kind of fairly standard to prove. It's not very difficult. So you have a measure in infinite volume, and the question is, does it have a symmetry breaking or not? Does it favors color 1 or not? And if the temperature is large enough, then it doesn't. Just the probability that the spin is 1 is going to be 1 over q. On the contrary, if it is below a certain critical temperature, then it's strictly positive. And then you have symmetry breaking even in infinite volume. Even if you send this boundary condition to infinity, you still have this field. So, this, you see, this temperature, this critical temperature is basically a model for this Curie temperature, because it's exactly saying a magnet is going to stay magnetized if basically spins have a tendency to point in the same direction, even if you have a lot of atoms in a magnet. So two spins very far from each other still have a tendency to be pointing in the same direction. If the temperature becomes too large, then basically you are in this regime, and two spins very far away from each other, they do not care about each other anymore, and they are pointing in different, in independent directions. So then the average number of spins pointing plus is roughly the same as an average number of spins pointing minus, and this is basically telling you that there is no global magnetization in your magnet. Okay, so this is exactly the intuition for the introduction of this model. But mathematically, it's not. We are not going to care too much about Curie's temperature. What I want now to study is what is happening at the different values of t. So for low t, for large t, and at tc, at this specific value. And these are simulations for the three values. So you see in this context, the color, the red color is a color 1. So this is low temperature, and you see that a large majority of vertices have a spin of color 1. On the contrary, for large temperatures, this is not at all true. It's completely independent somehow. Even very locally, you do not care too much about what are the spins, the colors of your neighbors. And at the critical temperature, there is something much more, much nicer than for these two things happening. It seems to be that there is some fractal structure occurring there. There is a very rich behavior. The geometry of the blue, yellow, the green, and red clusters is non-trivial somehow. So that's exactly what I want to study. I would like to understand what is going on here. And in order to do that, before doing that, I want just to give you maybe a few questions that are natural to ask on these models that maybe you are already asking yourself. So the first question is, Okay, what is the value of the critical temperature? Can you determine it? Experimentally, you can for magnets, but here for this specific model, can you compute the critical temperature? The second question is, I told you that strictly above the critical temperature, you have zero magnetization, you have loss of symmetry breaking. Strictly below, you have symmetry breaking. What is occurring at the critical parameter? Then, I mean, there you can imagine two things. Either there is ordering or there is disordering, but I mean, or symmetry breaking or no symmetry breaking. And if you think that this is just, you know, okay, this is just the value TC, I mean, it's only one value, we don't care so much about it, really think that in some sense this is by far the most important value. Because this is what we call a phase transition between an ordered and a disordered phase. And from the physics point of view, what you are interested in is how the system drives itself from a discontinuous or a disordered to an ordered phase to an ordered state. So this is exactly, and the way it does it is exactly going to be related to what it is exactly at TC. So this is the most fundamental value of T that you need to study. And that's good for you because from an aesthetic point of view, that's the nicest picture as well. So that's good. And the last thing, so the question which is related to what I just said here, so if I can understand whether the magnetization at the critical temperature is zero or not, then the next question is, well, if it's zero, in fact, then it's wonderful. I mean, from the physics and the mathematical point of view, then it's a beautiful world that is unraveling in front of you because the continuous phase transitions, they exhibit very rich geometric behavior. At criticality, you will have many beautiful things to study, and I will go back to this a little bit later in the talk. So then, this is somehow the beginning of the story rather than the end, because you can try to study, for instance, what are the fractal properties of this thing, what is the house of dimension, dimension of the interfaces and things like that. Okay, and let me start because I don't want to spend too much time on that by answering question 1. So question 1, in 2 dimensions, you can answer it. You can compute the critical temperature. There is something magical happening in 2 dimensions, which is called duality. You can explicitly compute the critical temperature. But that's the only value, that's the only dimension for which you can do it. If you go in higher dimension, then we do not expect even that there is a nice value. It's going to be just a real positive real number, and this is okay. I mean, you can live with it. It's fine. But I should just like to mention that, okay, it's defined completely implicitly in higher dimension. You cannot compute it. You cannot get a nice formula for it. And still, we are going to be able to say things about what is happening at this critical value, which if you think about it is non-trivial because you don't know where it is. So we need somehow to describe this phase implicitly. Okay. Before I proceed further, let me tell you what is the conjecture for question 2. So whether at criticality you have zero magnetization or strictly positive magnetization, whether you have symmetry breaking or not. So the conjecture is very nice, I mean, to my opinion, is that the phase transition is continuous depending on the number of colors. You could have thought that, okay, you know, I mean, why introducing many, a different number of colors, 2 is already sufficient, but you can actually get very different behavior depending on the number of colors. In fact, if you have less or equal to 4 colors in 2 dimensions, then the phase transition is going to be continuous. And if you have less than or equal to 2, so if you are basically the Ising model in higher dimension, it's continuous. Otherwise, it will always be discontinuous. That's the conjecture. So it's very much depending on the number of colors. And this is an illustration in dimension 2. This is simulation for 2, 3, and 4 state Potts model. And this is for 5, 7, and 9. And you see very well that here, no color is winning on the others. And there, in this case, actually color 1, which is now blue, is really preponderant. It's much more than density 1 over Q. So this is a conjecture. These are simulations. And let me just tell you for the specialists, maybe, just this slide, a bibliographical comments. So in dimension 2, the fact that this QC, this critical number of colors, is 4, was predicted by Baxter, so by a physicist, using what we call the exact solvability of the model. So he was actually able to compute the free energy of the model and to deduce heuristically a certain number of implications, and in particular to be able to predict what is the order of the phase transition, the fact that it's continuous or discontinuous. In higher dimensions, the consideration is that you compare your model to what it will be on the complete graph. You could imagine to define your model on a complete graph where you have really edges between every single vertices. And there you can compute everything explicitly, and in fact, you can guess that the phase transition is going to be continuous for 2 colors and discontinuous for more than 2. And then, in fact, you predict from physics that it's going to be the same in any dimension larger or equal to 3, which is something that may sound a little bit surprising at first sight, but which is the truth. What was known rigorously? So these are predictions from physics, but it's only at the level of the conjecture, and these are pretty old conjectures from the 70s, basically. So what is happening, what was known before what I'm going to explain? So one thing that was known is if you take the Ising model in dimension 2, then Onsager proved that the model is exactly solvable. Actually, this thing that Baxter is using for a slightly different model, Onsager was actually able to prove it rigorously for the Ising model and to compute really a lot of things about the model. And in particular, you can get fairly easily that the phase transition is continuous. So this is a very old work from the 40s. It's a beautiful work. It started a whole field of mathematical physics. So it's really a beautiful work. Then, in higher dimension, actually, you can prove that the mean field behavior is the correct one, in the sense that in dimension 4 and more, you can compare the model to the mean field behavior and prove that it has a continuous phase transition for the Ising model, for Q equal 2. So you see, somehow you almost have the full picture. The only embarrassing thing is that what is remaining is the most interesting dimension in some sense, because that's the physical dimension. It's dimension 3, which is the dimension in which, at least your magnets are living. So dimension 3 completely open at this level. On the other hand, for the discontinuous phase transition, what is known, well, I'm going to jump a little bit faster here, but it's known that for a very large number of colors, it's discontinuous. If you have really a lot of colors, then it's discontinuous. And you also know that if you have 3 colors or more, if you take the dimension to be large enough, then you are discontinuous. So these are only perturbative type results. It's not really, it's really not telling you much about the critical value. Okay, so this was the Potts model. I hope I managed at least to convince you quickly that it's not a completely silly model. And there is this main question that I want to try to understand, which is what is the order of my phase transition? But now what we are going to do is that we are going to somehow change completely our way of looking at things and transform our model via what we call a geometric representation to try to involve all the fields of mathematics in the fight. So we are not going to only work at with this model or with this Hamiltonian and so on. We are going to translate it into a model where, in fact, discrete analysis is going to come into the play. And in the second part of the talk, I will give you another way of transforming the model, where this time it will be probability that will enter into the play. So there is really these models. They are very rich in the sense that they give rise to very beautiful techniques from different fields of mathematics. So it's very exciting to work on this type of things. Okay, a motivation for what I'm going to do next. I think you all heard about some amazing progress that appeared in the last 15 to 20 years in statistical physics concerning the 2D critical behavior. So what happened is that some mathematicians, and for instance, Rick Kenyon and Stas Smirnov were two of the main contenders there, introduce certain average of random variables. So imagine you are on a graph, for instance. Let's give you an example which is not such a good one, but maybe still it's going to help you a little bit. Just take, for instance, a function f of x, which would just be the average of the spin at x.
See? So this is a function of the vertex. And you can look at its property as a function. And basically what Smirnov and Kenyon did for two different models, for the Ising model and for the dimer model, which I'm not going to define, is that they notice that not really this function, but function of this type are discrete holomorphic. So what does it mean to be discrete holomorphic? That means that basically it's discretization of a holomorphic map. And one way, if you want just to keep one definition in mind, just think it satisfies some discrete version of Cauchy-Riemann equations. So for instance, you could imagine this minus this is equal to this minus this divided by I. So it's like the partial derivative in that direction is equal to the partial derivative in that direction. So there is like that a notion of discrete holomorphicity, and they notice that certain observable, we call it, certain observables of our model are discrete holomorphic when you look at the model at criticality. Take the critical Ising model, take something that looks a little bit like the average of the spin at a vertex. As a function of x, it's a discrete holomorphic function. And they were able to use this to actually predict what is the large-scale behavior. If I take a very large graph, how this function should behave. And basically, they should behave roughly like holomorphic functions. So they were able to predict that and to deduce from this what we call the conformal invariance of the model. So I'm going to go back to this at the end of this talk. But let's just say that if you get conformal invariance, then there is a whole field of physics that become rigorous to you, which is conformal field theory. And once you get there, you can prove a lot of things on your model, really a lot of things. You can basically understand everything happening at criticality. So this is really the grail, is to actually get this conformal invariance. And, well, so this worked very well for the Ising and the dimer model, and it was like a lot of hope for everybody, especially that people found similar observables, similar average of random variables, which are almost discrete holomorphic for a much larger class of models, not only the Ising and dimer models. In fact, they were able to introduce what we call parafermionic observables, which were like really valid, appearing in many, many models, in particular in the Potts models. The only problem is that these parafermionic observables, they are not really discrete holomorphic anymore. So they are natural generalization of these observables that were introduced by Smirnov and Kenyon, but they are not discrete holomorphic. So somehow the game is not that easy because you cannot easily deduce conformal invariance. But in fact, one beautiful thing is that you can still extract information from this observable. Even though they are not discrete holomorphic, I'm going to tell you a little bit what they satisfy later in the talk. And from this, you can deduce still, for instance, that the phase transition is continuous. So that's exactly what I want to advertise in the end of this talk. But in order to do that, I need to tell you what a parafermionic observable is. And in particular, the parafermionic observable is not defined directly in terms of these colors. It's defined in terms of a slightly different model, which is obtained from this random coloring of the plane. And let me tell you a little bit how you get this new model. So step one, you start from your random coloring. So take a coloring. And between two vertex which have the same color, toss a coin. And if it and with probability 1 minus e to the minus 2 over t, just add the edge. And with probability e to the minus 2 over t, you do not add the edge. You never add an edge between two vertices which do not have the same color. So around every around every edge, you check whether you add it or not. And what you get when you forget the coloring is you get a subgraph of your original graph. Okay? It's the same set of vertices, just the set of edges is a subset of the set of the original edges. And then, that's step one. In step two, we are going to transform this into a loop model. So let's take the square lattice. Let's imagine this. Oh, maybe we don't see very well. I'm sorry about that. So let's imagine you have the blue edges are the edges of this graph. And let's draw what we call the dual configuration. So the dual configuration, you take the dual lattice. At the middle of every face, you put a dual vertex. And every edge of the dual lattice is in direct correspondence with an edge of the primal lattice of Z2. Okay? So what you are going to do is that for every edge of the dual lattice, you add it if the corresponding edge of the primal lattice is not blue, is not in this graph. Okay, so you do that for every edge. So you obtain your primal graph, the graph that you started with, the blue one, together with a new graph, the red one, which are somehow, it's a complement somehow of your original graph. In fact, the dual of your graph. Now what you do is just you draw the loops between the connected components of your primal graph and your dual graph. You draw all the loops. I draw them in a nice way, but it's just because it's convenient for technicalities, but just draw loops. And then forget your primal and your dual graph. Just forget them. So what you get is you get a family of loops. Okay? So from a coloring, by all these steps, you get to a loop model. And if you have a distribution on this thing, you get a distribution on this loop model. So you get a random loop model. Okay? So take this random loop model in a very specific context. So take a domain, simply connected domain, say omega, maybe I use D, and 2 points A and B on the boundary. And let's take a discrete version of this. So you just take, let's say you take the intersection of Z2, of this domain with Z2. Okay, so you get a subgraph that looks like your continuous domain. And you take A and B to be on the boundary of this graph. And now you draw the loop that I was talking about before, the loops, except that what you do is you force the loops to turn on the boundary of your domain systematically. If you do that, it's very easy to see that you get a family of loops, but the loop that is starting at A cannot stop. It's going to necessarily go out through B. So you get a family of loops together with one path, one curve from A to B. This curve, I'm going to call it the exploration path. And once again, if you had a distribution on random coloring, in fact, you can deduce a distribution on these loops. Now, what is the parafermionic observable? Well, it's going to be the following. So you have these loops. So there are all these loops like that. I'm going to take an edge, E, or a place in my graph, and I'm going to look whether the interface is going through, the exploration path is going through this edge. So I'm almost just looking at the probability that the edge is on my exploration path. If you think about it, this is a very natural quantity to look at if you want to understand the geometry of your path. You want to know what is the probability that it goes through a point. But what you do, and this is a twist, that you add this term, e to the I sigma times the winding. So the winding is a total rotation that the curve does between the edge E and the end of the curve. Now it's going to do a certain total rotation. You count it in radian, and you just look at e to the I sigma times this quantity. So it's some kind of spinner. It's changing a little bit. You don't count just the probability. You twist it with this winding term. It's not very important if you do not get why we are doing that. Actually, it's not really even very important for us. The important thing is the following, is that if I look here, I just look at this observable just at any temperature. You start from the Potts model. You transform it into a loop model. You look at this, basically the probability that an edge is on this exploration path. You get a certain quantity. It's a function of the edge. Now, if I look at the critical temperature, and if I tune sigma to be equal to a very specific value, I want sigma to satisfy this quantity, so Q is a number of colors, remember. If I do that, then this observable f, as a function of the edge, satisfies a very specific property. It's going to satisfy that the integral, you have a natural notion of discrete integral for this function. Well, the integral along any discrete contour is going to be 0. I don't want to define, I don't have time to define what a discrete contour is, but here I just want to draw your attention on something which is, this looks like a discrete version of Morera theorem. If you think about Morera theorem, if you have a continuous function with discrete contour integrals is 0, it is holomorphic. Well, here it's some kind of discrete version of that somehow. So we do not call it discrete holomorphicity because, in fact, it's a little bit weaker than the standard definition with the Cauchy-Riemann, the discrete Cauchy-Riemann equations. It doesn't give you as much information, but you should really think at an intuitive level that this is a discrete version of this, discrete version of holomorphicity. So there is something very magical here. So there is really this specific random variable, which is very weird with this winding term. You average it, you look at it as a function of E, it almost looks like a holomorphic function. And in fact, it looks like this only at the critical temperature. And this fact, you can use it, it's not trivial, but you can massage all this. I mean, this is a nice property. You can try to use it, and you can prove that, in fact, it implies the continuity of the phase transition for 2, 3, and 4 colors. So in some sense, it's really optimal for half the conjecture. You can get the continuous phase transition for this. And this is really, you see, I mean, I started from a planar configuration, so it's really for the planar Potts model. And if you are asking whether Q equal 4 is related to the 4-color theorem, this is not the case. It's rather related just to the fact that you see here, to solve this equation, Q equal 4 is very specific. Why? Because if Q is smaller or equal to 4, sigma is going to be just a number between 0 and 1. It's going to be real. And if sigma, I mean, if Q is larger than 4, then it becomes actually a non-real number. So this is a quantitative difference. So it's always a little bit disappointing that there is no connection to random color, I mean, deterministic coloring. It's really something different. Okay, here, I mean, of course, I didn't expect you to be able to follow really what I mean, to really understand why this is working. But the only thing, like the go-home message, if you want, is really the fact that we involve analysis, basically. Here, there is no probability. We are looking at no averages of quantities, but we are looking at it from an analytic point of view. Actually, a holomorphic, I mean, a complex analysis point of view. So by mapping it to this loop model, we involve analysis. Let me just finish this part of the talk by telling you a little bit more about what you can do next. Why is it natural to get these holomorphic functions? Why do they pop up in this model? And the reason is very deep, in fact, is that if you look, I told you, look at your domain D and look at the square lattice approximation of this. But imagine now I tell you, okay, look at a square lattice approximation, but with very, very thin mesh size. Take delta much smaller than 1, look at a very fine square lattice, and look at the approximation of your domain in this lattice. When you do that, you have a random model, so you have a random interface, a random exploration path between A and B. Well, what is the limit of this random path when delta tends to 0? And the conjecture by Oded Schramm is that it converges to a Schramm-Loevner evolution. And these are examples of Schramm-Loevner evolutions. And one beautiful fact about the Schramm-Loevner evolutions is that they are conformally invariant, in the sense that I gave you a domain D, my favorite domain D, 2 points on the boundary, and I told you take this limit when delta tends to 0 and look at the limit of this exploration path. It gives you this exploration, I mean, it gives you this random path from A to B in omega, and note that this random path is very nice. It has some fractal properties. Well, I could also tell you, okay, use the conformal, use Riemann mapping theorem, take a conformal map it to your favorite domain, and maybe it's a disk. Well, in this new domain, you have 2 natural curves that you can construct. First, you have just the image of this one by the conformal map, but you could also just look at your model directly in this domain, take a fine approximation, let delta tends to 0, you get a priori another curve, another random curve. Well, conformal invariance tells you these 2 curves, they are the same. They have the same curve in law. This is extremely intuitive if you take just a rotation by pi over 2, because this is already a symmetry of the lattice. But what I'm telling you is that it's true for any rotation. any angle. And in fact, it's true even for many more maps. You can take any conformal map. And this, at least as a mathematician or a physicist, when you see that, you are very happy because you have a lot of symmetries in your model. So it's a much simpler model to study, and you can say much more things about it. And indeed, if you have conformal invariance, you are able, as I said, to derive basically everything you wish on the critical phase. So this is a beautiful conjecture. And let me say that the observable that I introduced just before, this strange observable, in fact, when you look at it in this domain and you rescale it properly, it should converge indeed to a holomorphic function. So this discrete holomorphicity translates into really holomorphicity in the continuum. And in fact, it's possible to guess what is the limit. Let's ignore what is exactly the expression, but you can guess what is the limit of this observable. So if you want to prove conformal invariance, and you really do want to prove it if you are living in this area, well, what you want to do is to improve this property to make it more, to make it stronger in such a way that you can derive from it the convergence in the scaling limit, what we say, when we take the mesh size to 0. And if you can do that, then you get conformal invariance. And in fact, there is one value of Q for which you can do it, and that's the value Q equal 2. So for the Ising model, you can get conformal invariance, and it's a result by Chekhak, myself, Ongley, Kampainen, and Smirnov, that indeed this path, this exploration path that you have, you can compute, you can prove that it converges to the Schramm-Loeffner evolution of parameter 16/3. And once you have this, in fact, you can also get the many, for instance, the geometry of the interfaces between pluses and minuses in the Ising model and so on. So you can get a lot of things from it. And let me say that the main tool here, the main step, is really proving this conjecture for Q equal 2. So this is the end of the first talk. It was more of an overview. I went fast on many things. Now what I want to do in the second talk is really I'm going to use the board, and I'm going to present another representation. Here I transform it into loops. In this second part, I'm going to transform, I'm going to involve the notion of random current. And from there, I'm going to try to derive a few properties of the Ising model in this case. And in particular, one of the goals of the second part is to try to tell you a little bit more about what is happening in higher dimension. And basically, how you can prove that in dimension 3, the critical, the phase transition is continuous. So I'm not sure I will have time to go up to these points, but basically we are going to change the geometric representation, prove all, it's going to help us in a completely other way. We are not going to involve analysis. It's going to be mostly using probability, and try to see what we can do for it for the Ising model in dimension 3. Okay? Thank you very much. This is just to guarantee that I have a question. So this is the Rhône, and this is the Arve. So it's in Geneva. You can recognize it by this thing here. And so this is coming from the lake, and this is coming from the mountains, from basically Mont Blanc. So it's coming from Mont Blanc, so it's muddy water, and this is very clean water. And you have this very nice fractal interface between the two. And what you have to imagine that here it's maybe 30 meters, but it lasts for kilometers, in fact. So it's a very nice interface between the two waters. They do not mix for a very long time, and they have this very nice fractal behavior at the interface. Yes?
I know this doesn't help you at all, but you do have those other values of the parameter. Is there any use to that? Is the Moreira-type theorem hypothesis true for the...
You mean which parameters?
The values of sigma raised constant?
So for this model, there is no other value of sigma which is interesting somehow. There is a very fine tuning between the value of sigma. In fact, the sigma has an interpretation of a spin, and it's related really to the universality class of your model. So it's, sigma, you don't have so much. Actually, you can predict it before checking that this is the only guy that gives you this very nice property. So there are no other values for this specific model. For the ON model, you have two nice values, and then you can use the two values, and they correspond to fixed point of the renormalization group. But that's very a different story. For this case, you have only one.
So you're saying that case is actually false when Q is complex, and you have this equation. If you solve that equation,
If
Q equals 5, say,
yeah.
is that a complex number?
You get also you get also that for Q larger than 4, you also get this relation. It's just that there it doesn't really interpret as a discrete holomorphicity. It's really, in this case, you don't have such a nice interpretation. But you are right, it works very well for the higher. I mean, somehow it's still interpreted, but just the observable is trivial in this case. It's going to converge to 0. So it's a holomorphic map, but not the most interesting one. That's the point.